morning, everyone. Welcome to this session, doctoral meeting session on our Space Science and Technology PhD program. I would like to thank you all, our 7 speakers today, and all the audience, including the supervisors, for being here. Today, we're going to be discussing, talking, and listening to the presentation of the PhD students that are working on different problems related to astrodynamics, space tethers, also space debris, GNC problems related to space, etc. Right, so it's quite interesting topic. We have also some industrial PhD thesis, some academic PhD thesis, and I hope you all enjoy. Okay, so sorry for these minutes of delay and these problems with the connections, but I think we are all here now. We're gonna start with Luca and Sadaf. They're gonna be presenting topics on space tethers, right? And then we will continue with Sergio and with the other established before. Okay.
Okay. Hello everyone, and good morning. This is Sadaf, and I'm going to talk about my thesis with the title of Modeling Emission Analysis of Low Work Function Tether under supervision of Professor Gonzalo Sanchez. First, briefly, I talk about the main concept of our work, and then I will explain about the methodology we are using and its limitations. Then the improvement we have implemented to remove these obstacles, and afterward some selected results will be presented, and finally the achievement we have obtained so far and the future activity plan will be addressed. My thesis has been funded by E.T.PACK project, and as Lucas said, the goal of this project is to develop a deorbit kit based on electrodynamic tether for the end of life of the satellite. And in this project, the mission analysis and performance determination will be carried out by electrodynamic tether simulators, where the Lorentz force plays a significant role in the simulator. And to compute the Lorentz force, we have to model the current voltage profile along the tether and compute the average current. And to do so, we have to understand and model the plasma structure around to the object. A few years back, Gonzalo and Shin presented a stationary Vlasov-Poisson system for emissive probe in cylindrical geometry based on orbital motion theory. In this model, the plasma is considered to be unmagnetized, collisionless at rest, and Maxwellian and half Maxwellian distribution function are considered for plasma species and emitted electrons respectively, and trapped particles are ignored. Due to the assumptions of this model, the distribution function, transverse energy, and angular momentum are all conserved along the particle's orbit, and which leads to write the Vlasov-Poisson system as a single integral differential equation. And after discretization, this equation becomes a set of nonlinear algebraic equations. This set of equations then can be solved by the iterative scheme of Newton-Raphson method. Using this code, the current voltage characteristics of cylindrical emissive probe could be computed, and different operational regime also could be identified. However, this approach had a drawback, which was high computational cost, and mainly due to the computation of the Jacobian matrix in the Newton method by finite difference. So as a result, deep parametric analysis also was not possible. The goal of this thesis was to improve the algorithm, and the effort that we have done so far was mainly related to improvement of the algorithm. So in the first place, the Jacobian matrix in the Newton method was computed analytically. I don't go into the detail of the mathematics, but I should say that this part hastened the code by factor of 100. And then we implemented the parallel architecture. So in this architecture, each processor takes care of computation of mesh point, each mesh point in current voltage characteristics, and also the selection of these mesh points was in a more efficient way. I mean, in a third place, we use an algorithm to select these mesh points in more efficient way, where these mesh points are more close to the transition boundaries. Finally, the code func-C was developed, and taking advantage of this code, a large database has been constructed, which contains over 18,000 current voltage characteristics in HDF5 format. This database covers a broad range of physical parameters, the dimensionless physical parameters we have in model, which are 5, the probe bias, emission level, emitted electron to electron temperature ratio, ion to electron temperature ratio, and probe radius to the bivalence. Using the new code, finally we were able to parameterize the IV characteristics and different operational domains. We also provided a software which includes 140 solutions and some MATLAB codes to extract useful information such as macroscopic quantities or the operational domain in parameter space, which is accessible in a public repository of the university. Here you see one of those 18,000 current voltage characteristics we computed, and different operational regimes are identified. And for example, in the inset, you see the potential profile of in inset B, the region is space charge limited, or for example, in inset A, you see the non-OML and OML regimes. Here also I want to show you some selected results. The operational domain over emission level in bias and emission level plane. So we captured the different operational domain, OML, and space charge limit, and the other area is non-OML. The OML region is where we captured the maximum, and the probe captured the maximum current, and the space charge region is where the emitted electrons are reflected back to the probe. One of the novelty of this work is finding this close OML region. And also on the right, you see the different operational transition boundaries in radius and bias plane. And here we compared our result with San Martin's result, and which is it shows promising results for a tether application, because the OML region is larger than was expected before. Taking advantage of numerous solutions in the database enabled us to provide some analytical laws for space charge limited boundaries in parameter space for both positive and negative bias, and this analytical law will be used in a tether, lower function tether modeling. We also propose an analytical law for current drops in space charge limit regimes for emitted electrons. Actually, the ratio of the current we emit and over a total current. We also revisited some experimental methods in plasma diagnostics because the database that we have constructed is not only applicable in tether technology but also in plasma diagnostics. So we revisited some methods such as separation points, inflection points, and a floating potential, and we proposed an analytical law for the latter. Here I listed our achievements so far, including participation in a conference, submission of the manuscript. The code Funksi has been registered by UC3M, and the developed software was published. And recently Gonzalo presented our work in a SPIN meeting, and I think people really liked our work, and one of the professors from University of Alberta suggested to developing an algorithm to extract plasma parameters from current voltage, experimental current voltage characteristics. And we are going to set a meeting and investigate possible collaboration. So finally, when we have a model for a plasma structure, so we can develop a semi-analytical model of current voltage profile along the tether to compute the average current and Lorentz force, which takes part in a flight simulator to determine the performance of the lower function tether. However, as you may know, the tether technology is propellantless and also reversible. It means that it can work in a drag mode and also in thrust mode if we place electric power inside the satellite. So as a second step of my thesis, I'm working on a lower function tether in thrust mode for a station keeping scenario, and my goal is to optimize the tether system size. This part of work is progressing. And thank you so much for your attention. If there is any question, I would be glad to answer.